So for this lesson, we're going to start off with a graph. Here we have graphed y equals sine x divided by x. Right, so we're trying to find the limit as x approaches 0. And if I put the cursor here at 0, if I can hit it. There we go. Whoops, almost had it. You can kind of see it. It keeps flipping around all over the place. There it is. All right, so you can see that at 0, our function y equals sine x over x is defined. We can't plug 0 in. All right, but it does appear, if we look from the I should start to say the left-hand side. If we look from the left-hand side, see those numbers are getting closer to 1. That's pretty close. And if we look at the right-hand side, notice those numbers again are getting very close to 1. Right? But we want to find, oops, where's my page? The limit. Let's pull up my page again. Here we go. So we've graphed it, and we saw that it looks like it might be 1. But we want to actually be able to find this algebraically, not just graphically. So we can't plug, obviously can't plug in 0. Can't do substitution. So we might try to prove this using the sandwich theorem. Right? Because remember, sine is limited, right? It oscillates, it goes between -1 and 1. That's it. Right? And so we know it's sandwiched in between -1 and 1. Right? So if we were to take our function there, y equals sine x over x, that would be in the middle there, right? And if we were to make one the opposite, make one the positive, we end up with, on the opposite side, -1 over x, and on the other side, 1 over x. Right? So now our function is sandwiched in between. But remember the sandwich rule, the sandwich theorem, the whole point of it is to have a limit that was easier to take. Is 1 over x any easier? Well, no, because it's not defined either. Right? So we can't take the limit as x approaches 0 of 1 over x or -1 over x. So it seems like a really good idea, right? Because we would have our two functions that are, this is sandwiched in between, right? Because if we multiply something by sine x, it's going to make it, the most it's going to make it is 1, and the least it's going to make it is -1, and everything else is going to be in between. So it seems like a really good idea. However, we're not going to be able to find the left and right hand limits using this, right? So that's not going to work out. So we're going to have to be more creative. Just see if you can follow this proof. Don't worry, you wouldn't have thought of it, right? Just follow along. And it's a rather creative use of the sandwich theorem. All right, so we have here graphed sine theta. We have that graphed instead. All right, so we know that when we're looking at any point on the unit cosine, right, because cosine uses adjacent, and the y coordinate is sine, because sine uses opposite. Right? So here we just have a random point, x, y, right? And so x would be the cosine, and sine would be, and y would be the sine of that angle. All right, so let's continue on. Right? So our radius, we know, is 1. Right? So I'm going all the way out to the radius here, because we're on a unit circle, and we've created a new triangle. This particular triangle, that red side there is 1, because that would be the unit circle. And I've just continued what was the hypotenuse of that triangle. I just kind of continued it until those two sides met. The x-coordinate would be 1, right, because we're 1 unit out. The y-coordinate is going to correspond to whatever tangent theta is. Right? Because we're looking here at this length, this AT. Right? And then tangent is the one that's going to use the opposite and the adjacent. But the adjacent, that's just 1. Right? So essentially, if we take the tangent of that angle, because the adjacent's just 1, right, we're going to have that measure there can be related to tangent theta. Let's continue on. This one's very visual. Remember, this whole thing is very, very visual. All right, so now we're defining the sides here in a triangle. All right, so cosine theta would correspond with our x. Sine theta corresponds with the y, right? Tangent theta is going to correspond with the y, but for the larger triangle. And we're continuing on. Right, so here we have one triangle. We have triangle AOP. Notice it's not a right triangle. Right? We know one side, we know this side. Right off the bat is 1. Right? That side is 1. We also know, look at that, that side will have to be 1 as well. Right? Because both of those are radii in a unit circle. And then we have the other side, and who knows what that is. Also, if we were looking for area, what we would use is this value right here, right? Because this would be the height of our triangle. Good to review that from geometry. So that would be the height of our triangle. And moving right along, there it is, height of our triangle. All right, so now we have triangle, area of triangle AOP. Right, so that was our triangle there. Is going to be less than or equal to area of sector AOP. And you see the triangle there ends at the dotted line. The sector of a circle is, it's kind of like a piece of pizza. It's a portion of the circle. Its sides are radii, so it's bound by radii and the perimeter of the circle there. So it goes right to the outside, right to the edge of the circle. So of course that's going to be a little bit larger, right, than the area of the triangle. And both of those are less than the area of the big triangle, triangle OAT. That's the biggest of all, right? So that's easy to see, right, the ordering of our triangles here. All right, so now let's figure out how to find the area of the triangle. Now I said we would normally use altitude, right? We would use the height of the triangle. However, what's the height of the triangle? I don't know. Do you know? Nope. But we have another method. This will come up every so often. Cover this in geometry because it's useful. And this is, I want you to write this in your notes. It is Heron's formula, and it is another way to find the area of a triangle. And it's any triangle. That's the beauty of it. It's easy to find the area of right triangles. It's those other oblique triangles. This one you can use to find the area of any triangle. So remember the area of a triangle. Normally, if you're just using that, you know, that formula you learned in elementary school, it's 1/2 area of the base times the height. So the 1/2 is still in there. We don't necessarily know base and height in this particular triangle. Well, we'll know base, but we'll know one side. We know the sides. We just don't know the height. All right, so rather than thinking of it as base and height, we have two sides we know. Right? The A and the B there, they're both 1. There's a relationship between the area of the triangle and the lengths of any two sides and the sine of the angle in between those sides. So it has to be two adjacent sides and the angle in between, right? The included angle, right? And we can use that to find the area of any triangle. So I want you to have that in your notes. All right, so we have 1/2. Let me write this a little nicer here. So we have 1/2, because that's part of the formula. And then you have A, which is 1, and B, which is 1, and then the sine of the angle there, right? So that gives us the area of the triangle that we see there, triangle, whatever its letters are, AOP, OAP, AOP. All right, so now we're going to look at finding the area of the sector AOP, and so we're moving along. All right, so area of a sector, right? You remember back from geometry, right? It's a portion of a triangle, so excuse me, a portion of a circle. I got triangle in my head, right? So area of a circle, right, is pi r squared, right? And so if we wanted just a piece of the circle, not the whole circle, right? We would take the measure of the central angle over 180 degrees but we're doing it in, excuse me, over 360 degrees, but we're doing it in radians, not degrees. So instead of having 360 degrees, I'll write that in there. I'm always better when I write. Area of a sector. So this is back from geometry. Right? The area would be the central angle over 360, because that gives us the fraction of the circle. So we don't want the whole thing. And then times pi r squared. Okay? This would be for degrees. But we're not working with degrees. Right? We're going to work with radians. So what's 360? Well, it's just 2 pi. Right? So it's the same formula from geometry, except instead of 360, it's 2 pi. Right? Now our central angle, that's just theta, right? It's marked as theta. Our radius, that's 1. Right? So now we're going to plug that to find the area of the sector. So it's going to be theta over 2 pi times pi r squared. We can cancel out the pi, right? So the 2 pi, that's from trying to equals, oh yeah, that's, so I have it over here for the reduced one. Following along with my handwriting from before. All right, so we can cancel out the 2 pi's, right? You can see it right here, right? You can cancel those out, right? It's one in the numerator, one in the denominator. So we'll end up with central angle, that thing is an angle, times the radius squared divided by 2. Our radius is just 1. So now that becomes our central angle, which is just theta over 2. So now 1/2 times 1 times sine theta, or we could seriously just write this as sine theta over 2, doesn't that look nicer, is less than or equal to theta over 2. Right, now we need the last part of our formula here, and that is the area of the triangle oat. And guess what? That's going to be on the next page. So by the way, you have this in your notes. Just, you'll match it to the picture and do a fill-in. It's not exactly, but it's pretty much like mine. And write in everything that you see. All right, so we've got, let me make this a little simpler again. So this is just sine theta divided by 2. That's going to be less than or equal to theta divided by 2. Now we need the area of our triangle. Now we can go back to that old formula, area equals 1/2 base times height. Okay? This is a right triangle, right? Because that is a vertical line. All right? So now we can just use that formula, and we know the two sides, right? We don't need the hypotenuse, that's not part of the area formula. We know that we have values for those two sides. The base is 1, the height is tangent theta. So now we can use that one. And so that's going to be less than or equal to tangent theta divided by 2. I'm just going to simplify that up a little bit, right? Because 1/2 times 1 times tangent theta is the same as tangent theta over 2. So now we have an inequality to work with. And we know that our theta divided by 2 is going to be sandwiched in between the other two. All right, so here's our formula again. All right, and so we have, I'm just going to write that again a little nicer. Sometimes my handwriting is better than my typing. And this was tangent theta over 2. All right, so if you notice, everybody's got a 2. So we can just multiply by 2 and get rid of that. I think it's even easier to see that they're all divided by 2 when I rewrote that there. So all the 2's are gone because we're free to multiply an inequality by any constant we want. So now we have sine theta is less than or equal to theta is less than or equal to tangent theta. Well, how do we deal with that? Why don't we replace tangent theta with something with signs, like sine theta over cosine theta? All right, so now we have sine theta over theta is less than or equal to sine theta over cosine theta. All right, let's divide everything by sine theta now. Trying to get numbers here so that we can have something that we can actually work with in terms of being able to find our limit. All right, so now if I divide everybody by sine theta, look what happens. I've got theta over sine theta. Remember, we were trying to take the limit. This is our whole goal in my little visual thing here. Our whole goal was to take the limit, and I can put in theta as opposed to x. As theta goes to 0, of sine theta over theta. That's our goal. And look, we're getting closer. We've got theta over sine theta. All right, so if we divide everybody by sine theta, right, now we've got 1 is less than or equal to theta over sine theta is less than or equal to 1 over cosine theta. But it's not exactly the way we want it to be. We want it to be sine theta over theta. All right, well, you can do that with an inequality. You can take the reciprocals. When you switch it to the reciprocals, it does reverse your inequality. It reverses the direction of the inequality. Because essentially, it's like multiplying or dividing by a negative. You're not exactly doing that. That's why I say it's kind of like multiplying and dividing by negative. It switches the direction. So when we make it the reciprocal, it's going to switch the direction. All right? So now, just to make it look nicer, instead of having it going the wrong direction with the greater thans, all I did was switch the order here. So now we've got cosine theta is less than or equal to sine theta over theta, which is less than or equal to 1. We switched the ends. All right, so now sine theta over theta is sandwiched between two functions that we can take the limit of. I'm going to just move this here because this is like chicken scratch, literally. All right, so now we can take the limit of that. Things are going much, much better. All right, so because remember where theta was 0. All right, so we can, I don't know if I have this on the next page, but I'm going to do it right here. We can take the limit as theta goes to 0 of cosine theta. What's the limit as theta goes to 0 of cosine theta? Excuse me. Yeah, well, cosine theta. Now let me plug in. So, once we plug in, what is our limit of cosine 0? Right, that's just 1. That one works out. How about the limit as theta goes to 1 of 1? Well, of course that's 1, no matter what I plugged in there. The thing's a theta. I could have said the limit as theta goes to a gazillion, all right, and it's still going to be 1. When our function is 1. So now things are looking up for us because now we have a function. It is sandwiched in between two functions that we can take the limit of, unlike those other functions. And all it took was a little creative geometry. And creative is still creative meaning we used our head. There's nothing wrong with the geometry we did. Right? So now we know that if our function, so since the limit of cosine theta as theta goes to 0 equals the limit of 1 as theta goes to 0, and cosine theta is less than or equal to sine theta over theta is less than or equal to 1. The limit of sine theta over theta as theta goes to 0 equals 1. All right, using the sandwich theorem. Let me get rid of this. This is not really very important. Just wanted you to understand you'd have to switch the directions of the inequality. Using the sandwich theorem, or squeeze theorem, whichever you prefer calling it. And there we did it. We were able to take a limit using the sandwich theorem of something that seemed like we just weren't going to be able to take the limit of. And here I have it written as well one more time. All right, so we were looking for the limit as of sine theta over theta as theta goes to 0. The limit of cosine theta as theta goes to 0, that was 1. The limit as 1 as theta goes to 0, not 1, as theta goes to 0 is also 1. All right, so since our sine theta over theta is sandwiched in between cosine theta and 1. And the limit of cosine theta equals the limit of 1 as theta goes to 0. By the sandwich theorem, the limit of sine theta over theta as theta goes to 0 is also 1. Right? I want you to be able to understand it. It's not exactly a technique we're going to use to solve any limits with, what I've shown you here, but I do want you to understand it, right? Because this is what allows us to have a way to calculate out the limit for sine when any other method would not work for us. So know that we're going to, even though what we're going to be doing in the next part of these lessons may not look like the sandwich theorem, we use the sandwich theorem to get the original limit. And so now that we've got this limit, we can apply what we've learned to be able to work with sine. Right? So that's the whole point of this. All right, so your notes, I believe, kind of look like this with some nice pictures in it. So just a kind of a recap here. All right, we had the area of our three triangles, right? They're actually the triangle and a sector. So the smaller triangle was 1/2 sine, I have theta, not t. The area of the sector, right, that we used. So the area of the sector here, remember, this part here was our angle theta over 2 pi times pi r squared. The pi's would cancel. Okay? So that would be theta r squared divided by 2, but r was 1. And that's what gave us theta over 2. And then we had the area of our triangle. So this one here was using Heron's rule. And this one here was 1/2 times 1 times tangent theta, and that's what gave us tangent theta over 2. Right? And then we went through some more steps because we would have had to have changed this. So we didn't go right from 1/2 tangent theta to 1, right? We did a whole bunch more stuff in between, but in the end it went to 1, right? And we used the sandwich theorem. So this is just sort of a recap, not really to me a proof, but just a recap of what we did on all those other pages. And now that we've done that, we're going to have such an easy time of working with sine. All right, so the limit of sine x over x as x goes to 0 is 1. Oh, like, whoops, so I can find one limit. No, you can find many more. Not only is it sine x over x, it's sine ax over ax. So maybe x has got a coefficient. As long as we match in the denominator, we get to use the sine rule, and the limit's going to be 1. Right? So we've got some applications here. All right, so let's look at this one. Okay, not write in blue, but let's write in yellow. All right, so the limit as x goes to 0 of sine 4x over 4x, notice they match. Well, I shouldn't have changed to yellow until after I finished writing on the white. They match. So what's our limit going to be? 1. All right? All we have to do is remember what we've proven and use our property. All right, so here we want to find the limit as x goes to 0 of sine 2x over x. They don't match. We need them to match. You can't do anything to sine, right? Because this is parentheses, right? You can't touch that. However, you can do something to x. We want it to match. We could multiply it by 2. So that'd be the limit of sine 2x over 2x. However, you can't just go willy-nilly changing numbers. but I can multiply the numerator by 2. Now all I've done is multiplied by 1, right? Because 2 over 2, that's just 1. I haven't done anything bad to my function. I'm still mathematically correct. Now these match, right? I've got a 2x and a 2x. It matches. The limit of that part is going to be 1, and then we just have to multiply by 2. Right? So our final answer, the limit as x goes to 0, I'm going to move that 2 right here. 2 sine 2x over 2x is going to be 2 times 1, which is 2. Okay? I do want you to write out that times 1. Maybe it seems so silly. However, you're showing that you know the limit of the sine ax over ax. And that is important. So now that I spent all the time on the proof, now these problems are going really quickly. All right, so now we've got to get the denominator to match the sine expression. So you can change the number, you just can't change the sine expression. All right, so I want to change 4 to 3. What if we multiplied by 3/4? The 4's would cancel. I'd be left with a 3. Notice that we have a theta squared. That's okay. So long as we have a theta squared for sine, then we need a theta squared for the other part. So not only does it work with sine ax over ax, you can use it for sine ax, any exponent you want, so long as it's a the same exponent. All right, so now if we multiply by 3/4, we have the limit as theta goes to 0, sine 3 theta squared all over, those 4's cancel, and now this is also now 3 theta squared. But we can't do it to the denominator unless we also do that to the numerator as well. All right, so let's get a 3/4 in here. All right, so now we've got 3/4, and the limit for the sine 3 theta squared over 3 theta squared is going to be 1. So our answer now is 3/4. Please don't take shortcuts on here. Make sure you show that you understand the concept. You communicate that. And they get a little harder after a little while. We'll have to apply a little bit more things. All right, so long as we've got sine ax over ax, that limit is going to be 1. You can also flip it and have limit of x goes to 0 of ax over sine ax. All right, so you can flip it the other way. Right, so it has a lot more uses than just sine x over x. Right? And notice each time our limit is going to 0. But these don't match. Right? This is a 3. So we're going to have to multiply the numerator by 3/2 so that it will become a 3. If you do it to the numerator, you have to do that to the denominator as well. So you have the limit as x goes to 0 of 3/2. Oops, I did not mean to write sine. We have 3/2 times 2x. The 2's will cancel. That'll be 3x. Over 3/2 sine 3x. All right, so that's going to be, we're going to have this 3x over sine 3x, right? That's going to go to 1. But what about, notice our 3/2, that's in the denominator. This is technically 1 over 3/2 times 1. All right, so to simplify that, we multiply by the reciprocal, that becomes 2/3 times 1, or just 2/3. And there we go. Another one is done. And almost. Let's say I'm going to do 1. I'm going to do one more. This is the last one. All right, so now we've got 2 sines. If you cancel them out and say 7x over 9x, I will cry. I will cry very hard because you cannot do that. Cannot cancel sines away from things. All right, but what we have to do is split this into 2 values. So we have the limit as x goes to 0 of sine 7x, that's in the numerator there, times sine 9x is in the denominator. We need to match. We need to multiply by the missing ax in the numerator and denominator. So this one needs a 7x. The other one needs a 9x. But you can't go willy-nilly multiplying by 9x's and 7x's, right, unless you balance it back out again so that it eventually is 1. So there's 7x in the denominator. There needs to be a 7x in the numerator. There's a 9x in the numerator. There needs to be a 9x in the denominator. Now it balances. Essentially, we've multiplied by 1 twice. All right, so now we can find our limit. All right, so now we should reduce there. We have the limit as x goes to 0. We have sine 7x over 7x times 9x over sine 9x times, now you can cancel those x's as you should, otherwise they'll be indeterminate, 7/9. The limit of sine 7x over 7x as x goes to 0 is 1. The limit of 9x over sine 9x as x goes to 0 is 1. And then we have 7/9, whose limit as x goes to 0 is 7/9. And our final answer, 7/9. There we go. All right, so sandwich theorem came to the rescue and made a really complicated limit not so bad. All right? These are some whiteboard practice problems for you. I think there's just 3 of them. Super easy, right? And then we'll continue on learning more about trig limits. Thanks for watching. Bye for now.